Alrighty, welcome to another online meeting for MTH129 Discrete Mathematics. So this week I want to look at Boolean algebras. So basically a Boolean algebra is a pattern, I guess you want to call it. So a pattern. So the pattern is you've got a bunch of elements, and those elements have three different operations you can apply to it. One we'll call a multiplication, one we call addition, the other one we call sort of complement. And then there's two special elements, one called 0, one called 1. And they have various rules. And this is a pattern, and if you have a small set of rules that these properties uphold, then you get heaps of other rules coming from it. So it's some sort of neat pattern. So the two big examples of Boolean algebras we've seen is sets. So the plus corresponds to union, and the multiplication corresponds to intersection, and complement corresponds to set complement. And goes from there. So that's one big example. And indeed, any Boolean algebra is isomorphic, so therefore equivalent to a group of sets in some set. Or a field of sets in more general terms. So that's one big example. The other big example looked at is logic, where the plus corresponds to or and the dot, and the multiplication or dot, as you can see in this thing here, corresponds to and the overline or complement corresponds to not. So they're the two big examples, but you can see others. So I mentioned in lectures, binary digits and propositions, etc. And so although these sort of rules hold in general. So basically, what I'm going to look at is how can you deal with these sort of Boolean algebras. The main application that you probably most have in mind, if you're doing a computer science sort of subject, is logic and sort of logic circuits. So that's what I'll focus on today. So I've got here in front of me an expression. And so I would like to try to simplify it. And so, as I said, where you might want to use these sort of things in practice is if you've got, so if you're doing coding, which is logic, so which is one particular instance of a Boolean algebra, you might have a complicated expression that you have. You might want to swap the if and else clause, and so you have to take complements of stuff. You want to know how to try to simplify when you've taken the complement, etc. So this particular example is probably more than you'd ever really need to do, but knowing some of the smaller steps are important and will be useful too. Okay, so looking at this sort of expression as in any generic Boolean algebra, I would like to simplify it down. Now, if you are having trouble remembering things, two tips. One, you're allowed to bring a formal sheet in your exam, which is where these sort of questions will apply. So the example formal sheet I've put up online has all the rules listed, so that might be helpful too. The other thing is, if you can't, you often think in terms of the actual instances. So you can think of this as being in terms of logic or in terms of sets. So they're just the particular special cases, but they might help you remember some of the rules. So if you remember that overline means not, and the plus corresponds to or, and the dot corresponds to and you can maybe remember some rules that way. And that might help you understand what one particular way it's trying to communicate it as. But by no means the only way. So looking at this, the first expression here, the beginning bit, has got a not of some other common expression. So when you've got nots of other expressions, then the way to simplify those is De Morgan's law. And I think it's really helpful to remember it. You can look it up, of course, but it's good just to remember it. So what De Morgan's law pretty much states is if you get a complement of sum operation, you just do knots of everything in between. So I've got a knot, X bar, to put another bar at the top, Y put another bar at the top, and the operation changes. So it was plus here, now it becomes multiplication. Or before, now it's become and. So that's what De Morgan's law is. So it takes negation of everything and swaps the operator. Everything else is staying the same. Now I've written dots for multiplications, like our usual things, what we do with normal algebra. We can just omit the multiplications. That's fine. Now I can solve those different ways. When I've got double complement, I can just get rid of it. That's called the double complement law. Yeah, just a few things to say while I was writing this down is, I'm being rather verbose. I'm writing this down today. You could skip quite a few steps, and I'm about to in a second, as a matter of fact. You'll see why. But most of the time, I'm going to write down all the steps just so you can see what they all are. But again, you could do. Most people would combine these two steps in one line. Perfectly fine. So next, that first expression, the one I've highlighted, certainly looks much better now. It's using De Morgan's law. Now I've got this expression over here. Lots of x's and y's repeated. Although there's several ways of combining it, maybe just the simple approach of expanding the brackets might be a good first step. So expanding brackets, so you can expand brackets like you'd expect. So basically just multiply this number by both inside, and so you expand multiplication just like you expect for other numbers. You can also expand the plus as well, which is not so useful, which is not as expected. And that idea of expanding brackets, the fancy word, is called the distributive property. I'm happy in an exam, for example, if you just say expanding brackets or factorizing. That's the concept that we know, and that's the same idea, just different name for the same thing. So now we've got that. Now we're going to try to pull things together and make it look a bit simpler. Now, you could write down different ways. So the order of things doesn't matter. That's called the commutative property. So I can put the reorder things as much as I want to. That's x squared, if you want to think of it that way, and y plus x squared times y squared. And again, x squared, y squared are fine to write down. And that's, I'm using two things here really. So it's the commutative property. Being able to just move things around so freely when you've got lots together is also the associative property. And we're so familiar with things being associative that we can write it sort of buried down with everything else with no harm to what we understand it to be, and nor to any harm to anyone reading for that matter. Now, why I put all the x's and y's together is that one of the special properties is this idempotent property. And that when you do something to itself, you get the same thing back again. So anything with x and x. So x and x would just be x and y and y be y. That's called the idempotent property. So if you think in terms of algebra, which is what it looks like at the moment, x squared just equals x. In terms of a logic, for example, it's if you do something and itself, you just get the same thing back again. And although that's true, and that's true for multiplication like in here, it's also true for the sum. So you can see I've got one thing added to itself. So again, using this idea of idempotence, it's just the same thing repeated. So it's just the same expression or itself. So it's again idempotence. And so that whole thing on the right now is simplified, which is good. Now you're going to try to bring them together. And you go, oh look, there's an x in common, so I can factorize it out. And again, I'm happy to just say factorizing. The fancy way of expanding or factorizing brackets is this distributive property again. So, question. We've got this expression here. What does that simplify down to? So, Dylan, you're on the line. So, what does y bar plus y correspond to? So it's one of the special ones. So it's corresponds to 1. So if you think on it, if you want to have some help to understand what it is, so it's logic idea. So it's either not y or y. So it's either something happening so it's either something not happening or something happening. Well, it's one of the two's happening, so it either happens or it doesn't. So that's definitely true, and what we write down as true is 1. That may be one way of trying to remember it. So as I said, you can look them up when that's a standard rule, but in terms of help you reminding yourself, and that's called a complement property. A similar one would be if you've got something not happening and it happening at the same time. Well, that's not possible. So the similar sort of result, pardon me, is y bar dot y equals 0. So these two are called the complement properties. And you just have to remember plus looks like or, dot is something like the dot corresponds to something like and in one instance. And again, if you multiply anything by 1, no surprise, just get x. That's the again how we think of as 1. So that's the identity property. So the multiplication sum and the zeros and ones have been chosen so that although it's a pattern, lots of the rules match what we expect them to be. Not all of them, but at least lots of them do. And so some of them you have to think about. The ones that are a bit more surprising is this De Morgan's law and this idempotence. This idea that x squared is x in algebraic terms, when x plus x equals x. So, as you can see at the end of the day, we've got a compound expression and we've worked out the final answer is just x, which seems believable. That's pretty much about as simple as you can get. And so, as I said, I've written lots of lines here. You're more than welcome to combine a few together. Some are certainly natural to combine together. But make sure you get the final answer. And in your exam, I'm looking for some sort of working. And as you can see here, proving sort of things in Boolean algebra two different ways. But I made it clear I want to use the rules of Boolean algebras here. So that was some sort of approach like this was required. Okay. Different sort of thing is you can specify a Boolean function in different ways. You can specify it using expression like I just did in that past one, or you can do it in terms of value function. So if x and y, if you've got some various inputs, x, y, and z, then you can give a function. So functions which have binary inputs and a binary output can also be thought of as a particular instance of a Boolean algebra. And so we can use the properties of Boolean algebra to help us out. And so what you often want to do is you want to be able to go from an expression to some sort of truth table like this, or a truth table to a function, and vice versa. So a few different things we want to do here is, one, let's write as an expression. Now, lots of ways of doing that. The simple first step is called the disjunctive normal form. So that's disjunctive normal form, also known as the sum of products. which is a bit more illustrative of what we're actually going to do. And basically how to do that is you just look at the truth table, look at all the things that have ones in them, and then write down the corresponding expression as a product, and then sum up all the products, as the name suggests. So the one here would correspond to all of them being on. So it would be X being on, Y being on, and Z being on. That's the corresponding product. We'll sum up all these different products. So next product will correspond to the next one, which would be X being on, Y being off, and Z being on. The next expression would be this one here. So X being off, Y being on, and Z being on. And then we've got one more expression. What's this last one? So Dylan there, what would the product form for this particular row corresponding be? So it's X being off, so you really have to put X bar in, and Y being on, and Z being off. So it isn't Y by itself, because we also need to know that X and Z have particular value. So it's a product so these sum of product forms would have to have each of the variables present. So we've got three input variables here. Let's say input and output. So we have three input variables. So every of these product forms have to have the three variables, at least for the disjunctive normal form. Now that's the one way of writing. This is the default way of writing it down. As I said, one per thing. We want to simplify it down. So it'd be nicer if we could to write it down as just Y, for example, if that's what it really was. We want to try to simplify it down. So we're going to try to simplify. Now, you can use the rules of Boolean algebra to do that. So, for example, these first two terms, I could factorize the xz out. There's two terms in common. And the y plus y bar, just like we did in the previous slide, that equaled 1. And so these first two terms would combine to give you xz, which is simplification. So you can use the Boolean algebra. The more and more products you get, the harder it is to see how to simplify it down, I find. And so here's some other tricks to doing it. This is using a Carnot map, or K-map as I think they get called elsewhere. Carnot map. So how you work for a Carnot map is basically, I'm just going to write down the truth table that we just have. So this is our truth table. Just going to write it as a grid. So the truth table had 8 entries. So I've got 8 entries in my table. And I want to write it down so that I can easily pull out expressions from it. So on the rows here, I put say x, and the two values for x are x and not x, essentially. So x being on, x being off. And then I want to write down all the different possibilities I can get for y and z at the top. So I'll start with y and z. And then what I want to do to make it easier to pull things out, I want to make sure that when I go from one value to the next one in the next column here, I just change one value. So I got z. Let's just change the z. So that will change from z being on to z being off. That's just changing one thing at a time. And again, I want to change one thing at a time. I've just changed z, so I'll have to change y this time. So y bar, z bar, and again I have to change one thing. So I've just changed y, I've changed z again. And how these things work is if I changed one more thing again, I'd cycle back around. And so how this Carnot map, it's called a grey code. So grey code is every single expression here is adjacent to each other, so it's going to get one difference. And the great thing about this grey code, it wraps right around. So it's not in numerical order or chronological order or anything like that. It's in a way that's set up to be nicely be able to read off patterns from it. That's the whole point of it all. And that's not, sorry, the order, you can write the order differently if you wish, but it has to have that wrapping around idea and everything being adjacent for it to work nicely. So once you've set your grid out, and again, the format looks the same. So if you want to use this approach, you could write down that basic blank map in your formula sheet, if that's helpful for you. Up to you, if you don't want to have to remember it. But once you've got your thing, you need to put the ones in. And so there's a 1 for x, y, z. Here it is. So x, y, z is a 1. X, y bar, z. So x, y bar, z would be a 1 as well. X bar, y, z is x bar, y, z. And the last one, x bar, y, z bar is x bar, y, z bar. So basically, let's put the ones in where the ones are. And you can either leave it blank or put zeros everywhere else. So that's my truth table in a different sort of format, but in a way that's going to be easier to pull out the simplified expressions. So what I want to do is then I want to cover my ones, and just the ones, not the zeros, with blocks. And the blocks I'm allowed to use are rectangles, which have size of some power of 2. So in this case, size of 8, 4, 2, or 1. And the idea is you want to cover all the ones with blocks. That's required. You want to make the blocks as big as you can. And you want to have as few blocks as you can. So it's that. That's the sort of problem we're trying to focus. So the way to do that is just try to fit the biggest blocks you can. So what's the biggest block you can fit anywhere? And since there's lots of zeros, you can't put a block of size 8 or 4. So the biggest block you can really is a size 2. And there's several to choose from. So I'm going to pick this one to begin with as an illustration, and then talk about how to do other stuff. And I'll talk about some tracks with it all too, as for that matter. So this would be a block of size 2. So, and you've got every block, every power of 2 you increase. So if you increase it doubling each time, it reduces the number of variables present. So a block of size 1 would correspond to just one of these product forms, which is this case got 3 variables. When you've got a block of size 2, you can simplify down to just 2 variables. So the block of size 2 happens to correspond to these last 2 terms, for example. And just so how it is that how it's been designed is that 2 of the variables are in common. So you notice the x bar and the y is common to both these expressions. And you can see that from the map. So there's the x bar and the y's are common to them all. And how that's been set up, because they're adjacent, you get some things in common. And so algebraically, I could factorize the zz bar out, but the zz bar collapses to 1, which can sort of disappear out. So as you can see here, these 2 terms simplify down to just x bar y. And the way to see that easily, I find, my personal opinion, I find it easier to see that from the Carter map, saying I can see a block of size 2 straight there. Now we need to cover all the ones, so we haven't cut them all yet. So we've got 2 more ones to cover. And one of the properties of the Carter map is it wraps right around. So I can actually choose a block, which is the first one and the last one actually. It is a block of size 2, just wraps right around. And again, that corresponds to the first 2 terms here. And so that's how it happens. And so again, there's going to be some things in common here. And so the x is common to both of them, and the z is common to both of them. And so the expression simplifies to x, z. And the y plus y bar will collapse to 1, like I did before. And so my expression above now simplifies to x, z plus x bar y. Now, since we've covered all the ones, we can stop. So we've covered all the ones, so we don't have to go any further. So we don't need to put any more expressions down. And therefore, that is the most simplified expression you can get for this. Now, sometimes there is more than one most simplified. So there are several to choose from. But in this case, that's the best case. And so as I said, we want to cover All the ones with blocks, make the block as big as you can and as few blocks as you can. So a mistake that some people would make with this sort of thing, it's worthwhile making it to show why you don't do it, would be to choose as many blocks as you can. So you go, there's another block of size 2 just there, which as a matter of fact, you might have picked that before you picked the other red one. That expression, the YZs are common to both of them, and so that's YZ. And so some people might be tempted to put a plus YZ at the end. Now this expression here is equivalent to the other one, so they're all equivalent, so it's not incorrect, it's just not the most simplified form. And the reason is because these two, the one that's in green has already been covered by the other expressions, already been covered by the other blocks. So it's redundant, it's not actually adding anything more, and so I should leave it out. So the way I did it, it makes it look like you never think about it, but what you might very naturally might do in this case is you might do the blue block first, then the green block, and you don't have to worry about this other one. You go, oh, that's right, I can cover it with a big long 2, and that point in time you've actually, the whole green block only at the end is already been covered, and you go, oh, I can now remove it, and so you actually can take it out for redundancies. And you might quite naturally do that towards the end of the process. So in conclusion, the simplified expression for this function that we had defined for is given by this one here. And you can't do better than that. You could rearrange it to make it look like other forms, of course, but that's about as simplified as it gets. And so Kana maps are useful, and they could also be used in a very similar fashion if you had 4 input variables. That's getting a bit messy for an exam situation, so this is sort of style of difficulty you get in the exam, even though the technique generalizes to 4 variables nicely, 5 not so, because you run out of room to write everything down. So that's some things. So some things I want you to remember to learn out of this. So these are things I will ask you in your exam. Is I would like you to appreciate that Boolean algebras do have different instances. So I said sets, logic. I like you to simplify Boolean expressions using the rules of Boolean algebra. Like I did before, we able to prove a few things in general, and if we can apply them in special cases. Like you simplify Boolean expressions like I've just done here, using things like Kana maps or whatever you feel like, really. I mean, I'll often leave it up to you, but Kana maps I think is a good idea. And the other thing I want you to be able to do is, so one instance of a Boolean algebra is a logic circuit. So I want you to be able to do that. So let's convert this particular thing here into a logic circuit. So how a logic circuit works is you've got some input. So we've got X and Y as our inputs, and then we have an output at the end. And so we want to design a computer that does it. And so in some regard, these are implemented by transistors on a circuit board at some level, how it often works, or pathways in a microprocessor or whatever it might be, which is a bunch of transistors. So we want to write this diagrammatically before you chuck it in your hardware. And so this expression basically lets you think about what all the various parts are. So this plus here corresponds to an OR. The product here, and there's 2 of them, will correspond to AND. And the overline corresponds to NOT, or inverting. So now we're going to sort of build it together. So let's do the XZ bit first. So the XZ really is just going to be an AND between the X and the Z. So I should actually have 3 inputs to actually make it work. So with the X and Z, so I want to AND them together. So I've got signals from the X and Z putting in, And so the AND gate looks a bit like a D, something like that. So it's round on the edge, flat on this side, so big D. And so it's got X and Z coming in, and then X and Z coming out. So that's what an AND gate. The other expression we've got is not X and Y. So the first thing I have to do before I can do anything like that, I actually need to produce not X. So to produce the not of anything, you put it through an inverter, which is like a little triangle with a circle on the end. And the circle on the end is the biggest indication it's inverting. That's called an inverter, or a NOT gate effectively. So let's skip over that one. So I've got not X coming in here, and I want to have Y coming in. And then I want to, again, AND these. So I've got another AND gate coming out. So X bar, Y. So I've got two AND gates which give me these two product forms. And then lastly, I want to combine them together using an OR. So the OR gate is just a curvier form. So it's the back line's curvy, and then the front, instead of it all being a nice parabola, it's got a pointy form to it, which I always have trouble writing down, drawing. So that would be the OR gate. And so these two expressions I've got before now are fed in. That becomes our output of the OR of the two previous expressions. And so the things you need to remember are what an AND gate looks like. It's AND. An OR gate. And the inverter, which is not, essentially. So if you remember those three, now there are other sorts of these, as I mentioned in lectures, but those three would be sort of sufficient for all our purposes. And so this was important for hardware design at one point in time, and going between them. And so things like adding and and overflow of addition, etc., can all be done by these sort of logic circuits at the heart of it all. So anything to do with binary numbers, any functions of binary functions, which what this effectively is. So this is essentially a 3-digit binary number. You can do any operations of what a 3-digit binary number is, etc. So that's, again, one skill you want to do. And so I've got some examples more on that, but I'll skip over them. I wanted just to prove a few other things with Boolean algebras, just to show you some other things you might want to do. So these are some sort of other techniques of proving Boolean algebras, which I think are going to be some of the harder things to master. Well, that's my take on it. You might find all these stuff easy, etc. It's up to you. But so make sure you practice these logic circuits, drawing them and matching up to the pictures. But I want to prove some things. So first thing I want to prove is that the complement of 0 is equal to 1, and that's true in any Boolean algebra. I want to prove that sort of any Boolean algebra. So in the world of sets, for example, this would be the complement to the empty set would be the universal set, or in a way, not false is equal to true. Now, for those sort of cases, you go, oh, that seems obvious. If it's not false, it's true. But I want to be able to try to prove it in general. And so, sometimes proving the most obvious little looking results, it just seems obvious. How do you prove these sort of really obvious results? And can be a bit tricky. And you have to go back to what's really the definition of complement. So this is the definition of a complement, really. So the rules that really now satisfy, if you have two numbers which add to 1 and two numbers which multiply to give you 0, if you have both those rules, so these are the two complement properties, they together imply that they're complements to each other. Now, let's try to understand visually what's happening here. So let's just do sets, for example. So in terms of sets, that'd be if you got the union of two sets is the universal set. So visually, and the intersection of these two sets is the empty set. That's sort of what corresponds in terms of set. So in terms of a Venn diagram, I've got one set, XA, Y is some other set, so it's the rest, everything but the circle. Together, they form the whole. So let's just colour in. Y as best I can. Highlighting would be better. Yep. Okay. So X is the green set, Y is the yellow one. And so you can see together they cover the whole universal set, they cover everything, but there's no overlap between the two of them. That's what the two. So they combine, they give everything, but there's no overlap. If you get that sort of situation, then we call them complements to each other. So visually, that's what they look like. And so in terms of Boolean algebra, if you can satisfy those two properties, then bang, that proves they're complements. So that's what you have to do in this case. So, so first we notice that 0 plus 1 is equal to 1. And you go, well, why is that true? Well, it's the identity property using ones. So it's sort of the no, not true. Identity property of 0. So if you add 0 to anything, you get back to where you started from. That's the identity property of 0. Then you notice if you do 0 plus 1, again, that's sort of two things I want to consider, summing them and taking the product. That's equal to 0. And that's because that's the identity property of 1. So if you multiply anything by 1, you go back to where you started from. So these are two identity properties. So that's exactly what we want. So that implies that 0 and 1 are complements. So because you satisfy both those rules by the general rule of proving complements, that automatically shows they're complements. So in particular, the complement of 0 is 1. And incidentally, the other way around, so the complement of 1 would be 0 as well. Or not true equals false, in terms of logic, for example. So, although that came out really straightforwardly once we know it, this is the part that's worth remembering. And that is, to prove anything is a complement really involves proving these two rules just here. And that's the one that's worth remembering. And again, I use that concept proven to Morgan's law in lectures, but I just want to show it again to you here because I think that's something worth remembering because it's not easy to remember off the top of your head. Like you have to actually try to learn it. And so maybe writing on your formula sheet might be a good idea, for example. And I think the latest update of the example formula sheet has that on it, but I want to make sure it's there. So another thing I want to prove is the this one here. So x plus xy equals x. This is called one of the absorption property. To see what it looks like in terms of sets, at least. So I've got a set x and a set y. So the I've got the intersection of these two. So that would be x and y, or in terms of my Boolean expression, that's the x and y. So x intersection y is just the product of the two in terms of the Boolean algebra. So that's that bit there. And I've got x here. So x plus xy corresponds to the union. So it's combining them together. So visually, if I do the union of x and y, but since x and y is wholly contained in x, it sort of gets absorbed by it and will just be equal to x itself, which is what you see here. So this expression here is really just fully contained in x, so it gets absorbed by it. That's the idea of absorption property. And there's a similar one, swapping the roles of intersection and unions, or plus and multiplication, which I'll show in a second. So how do you prove it? To prove it really just boils down to proving that using the special case. So firstly, the special case is if you've got 1 plus y, plus anything at all, 1 absorbs y. So 1 is, again, in terms of sets, the universal set. So universal set union with anything else absorbs the universal set. So this is really the special case. This is a special case of x being 1. And this result here is, again, one of the standard rules. This is the special case. This is a special property of 1, which you could prove directly if you wanted to, but let's just hold it true. So that's one of the special properties of 1. So if you do 1 plus anything, you get to 1 again. So one of the special properties. And that's really 1 absorbs anything else, essentially. So once you've got that special case, then I can really reform this one over here. That's what I'm going to do. I'm going to multiply by x to generate the more general property. So I've got x multiplied by 1 plus y equals x times y1. And again, I can do a few things here. So I can do the distributive property to expand the brackets. And then I can use the identity property. So x times by 1 is going to be x. And again, these properties here are the at least ones that you don't have to think too hard about. So they're the obvious ones, you know, from normal algebra. So expanding brackets, anything times 1 just gives itself. And you go, bang, that's what we needed to do. So hence the absorption property. Now I did this in lectures not very well. If you've ever watched, if you watched it, so I've done it better today. So being able to prove some of these cases, sometimes using a Venn diagram visually does actually help. When you have to prove these properties, I really want you to better prove it in general, to all Boolean algebras, using just the properties, but using the special case of a set, for example, can help jog your memory or understand a bit what's happening. So by all means, use that sort of approach if you need to. But again, this absorption is, again, special case, this one here, for example. Just something else I want to talk about is the idea of a dual. So the dual of any Boolean expression at all, and basically involves swapping the ands and ors, or plus and multiplication, and swapping zeros and ones around. That's how you get joules. So this particular expression here, so the joule for it would be swap, there's no zeros and ones, I don't know if I wrote that, but you sort of swap the plus for a multiplication, and the multiplication, just there, by a plus. So the joule of this particular one would be this one in here, which is another. And so the two properties together, they are both of them are called the absorption properties. And so like most of the rules of Boolean algebra come in pairs, like you can see here. You go from one to the other quite easily, but if you know one Boolean expression is true, the joule is automatically true. And so this one's now true because the first one is. So the last thing I want to prove, if you know that x plus y is 0, then that implies x equals 0 and y equals 0. So putting in terms of sets, so this is the union. So if you know the union of two sets is the empty set, well, the only way that happens is if both sets are empty in the first place. That's what would correspond to sets, for example. So I want to try to prove that in general. That always would work on any Boolean algebra at all. And so where do you go? So we'll start. It's a direct proof. So this is sort of like the proofs we started with all the way back in topic 1. So I got an implication, a few different ways of proving implications. So one is just the direct approach. So show way 1. This is a direct approach. I'm doing this just to remind you the different proof tactics as much as anything else. So we start with that one. So now we're going to try to prove directly by a bunch of steps to get both these results. And what are we going to do? So basically, I want to just try to isolate just x to begin with, and I'll do a separate one to isolate y. So somehow I've got to try to isolate them down. So if you've got a union, to pull out, what I want to do is I want to pull out the x by itself. Well, in terms of sets, if you've got a union of two things, you just do the intersection of one set. That will just pull out the component you want considering. So that's what we're going to do here. So if you multiply both sides by y, that should extract x for us. And so if you look at this one here, for example, that's precisely we had a second ago. So x and x plus y just pulled at x for us. So that equals x by the absorption property. And again, thinking in terms of sets was helpful, at least for me, to do that. On the other hand, x times 0, anything times 0 gives you 0. So you can see that x equals 0. So just extract by using the intersection effectively, or multiplying by x, quickly gives you x equals 0. And in a similar way, multiplying by y will give y equals 0, which is what we need to do. So we've shown both x equals 0 and y equals 0, which is good. That's exactly what we're trying to do. That was pretty straightforward. I think that's nothing wrong with that. I want to just show you a different way. This is the proof by contradiction. I don't think it's any better in this case, or as a measure, I think the direct approach worked quite nicely. But I want to just remind you of different proof tactics because that's useful for your exams since we're getting closer to that. So how proof by contradiction works is we're going to assume the premises. So assume x plus y equals 0. So as always, and that's sort of granted. So we've got the premises true. Then we assume the conclusion is false. So what's the conclusion? So the conclusion is x equals 0 and y equals 0. So what's the opposite of that, essentially? So the opposite of an and, so assume x equals 0 and y equals 0, so the whole expression together, is false, aiming for a contradiction. That's how this is do. So the basic way to prove proof by contradictions, assume the premises, assume that the conclusion is false, then do a bunch of steps together to get a contradiction. So we have to translate some things here. So x equals 0 and y equals 0. If that whole thing is false, essentially we want the not of this whole expression. We've got not of an operator. That's when you use De Morgan's law. So De Morgan's law says we have to take the opposite of both of these themselves. So we've got x is not 0 and y not 0. And the and becomes an or. So with De Morgan's law, both of them get negated, and the operator gets changed. So and that's De Morgan's if you want to write it down what we're doing. So you can see this De Morgan's law is useful in many situations, by all means. So now we want to consider x plus y. So you've got x or y now. The whole thing is completely symmetric. So let's just, without loss of generality, suppose x is not 0. So, yep. So basically, I could do two different steps. I could do x not being 0 first is the first step, and then secondly, I could do y and b not 0. But I might as well do the same time, do them at the same time. That's what I'm trying to say here. So let's do them both together. We're saying, well, it's completely symmetrical. Just do one, and that the other case is going to be exactly similar. That's my little, and so the sort of code for that is saying without loss of generality. So now I want to get this contradiction. So I want to consider x plus y, essentially. And so if this is if you've got something non-zero here, if you're going to add it, this will also be not 0 since x is not 0. Now, is that clear enough? Like if you went to go for more extreme, if x was 1, for example, so 1 plus anything is 1, so it would be very clear, which is what I was thinking of when I thought of it before. But that's also true. So if you've got a sum of two things, if you know that if it's a union of two things, effectively, you're always going to get something bigger, essentially. So adding will always give you a bigger element. So if you've already got something which is non-zero, adding onto it's only going to get bigger still, essentially. So if you've got something non-zero, adding onto it can never make it 0. So we've got x plus y non-zero, but we also know that x plus y equals 0, so they can't both be true at the same time. Hence, our contradiction. Now, I think in this case, the direct approach is probably cleaner, but you can show, I just wanted to show that proof of one contradiction. Assume the premises are true, assume the conclusion false, do a bunch of steps, get my contradiction, essentially. And it's a useful technique in many situations. This is one that's almost appropriate for, I guess. So I guess the last thing would be, what's the dual for it? So what's the dual of this particular statement? You want to have a go, Dylan? See if you can write the dual. So as I said, the dual, as you're having a go at it, is swapping zeros and ones and swapping pluses and multiplications, or depends on anything, but ands and ors, intersections and unions, etc. Any ideas? And then anything, all the other things, you just leave as it is. Now, I'll do this one. So it's the plus becomes multiplication. You got to swap the zero, so the zero become a 1. So that's the x plus y equals 0 would correspond to x times y equals 1. So really swapping the zeros and ones, the plus and multiplication around. The implies still stick the same, x stays the same, but the x being 0 by the dual become 1 instead, and the y equals 0 would become y equals 1. So again, swapping those zeros and ones idea. And the and actually stays there. So we're actually just doing the dual just to the operators, just the expressions themselves, not the other sort of things we've got around. So what this one says, if we know that if you know the intersection of two sets is the universal. So in terms of sets, if you know the intersection of two sets is the universal set, that implies that both sets are the universal set. So in terms of a picture, so your two sets here, if this overlap happens to be everything, right, that's what it says. So if the intersection of two happens to be equal 1, if that's the overlap happens to everything, the only way that have to happen is if both sets were everything in the first place. That's sort of the dual result. So again, dual swapping pluses and multiplication, which I think you worked out, but also swapping the zeros and 1 around as well. And so, I mean, this one's a bit more complicated one to take duals of, because it's got the other funny operators in there too, but that same principle applies all the time. And we don't actually have to prove it, really. I mean, the proof is, I mean, there is a proof. The proof is because the original result was true, therefore the dual result's automatically true. That's it. So that's just a few things take away. So you do need to understand this idea of duality. So make sure you practice that, as well as just trying to prove some things. And again, if you understand some instances of it, like logic, and also sets, helps you through it. So I think in practice, you're probably going to be using more Boolean algebra stuff in terms of just truth, false values, just truth propositions. But sometimes it might be helpful to understand stuff of that when you go back to sets. So knowing there's a correspondence between all of these sort of things can help you, I find, with all, because sometimes the pictures of a Venn diagram make it much more easier to understand things. So that knowing the connection is really helpful. So I hope that was helpful today. So my plan for next week is just to do revision. So in lectures, I'll go through sample exam. There's 2 sample exams, so I'll go through one of those and just other general revision in lectures. So I was hoping for this time next week is to people have questions. So whether that works or not, we'll see. Um, so in particular, um, who is going to come with questions you want me to have a look at. So the exam's not long after that, effectively. So what things do you really want me to cover? I can't cover everything in an hour. So let's cover the stuff that you want help with. Um, and so I can do a really quick overview of the exam, but I'll just spend more time than the lectures than anything else. So I want to spend most of this time next week of just going, well, what's some aspects that you need to help with? What questions you want to cover? So have a think through. Better send through beforehand, etc. So I'll put an announcement to encourage other people to do the same. But anyway, I hope that helps. Any other questions you've got right now before we go? Awesome. Well, thanks very much for coming.